All right, let's get right into it. Today we're talking about one of the most classic, powerful, and honestly, one of the most dangerous vulnerabilities out there, the injection attack. It's all about tricking a system into doing something it was never, ever supposed to do.
But, before we even touch a line of code, let's start with a really simple analogy. We're going to see how a clever little trick on a librarian can explain the entire idea behind this massive cybersecurity threat.
So, picture this. You walk into a library and you've got a mission. Get every single book off the shelves, but you only get one shot, one request. How in the world could you possibly phrase that? It sounds impossible, right? Well, not quite.
Okay, so look at the difference here. A normal request is straightforward. Hey, find me books by Shakespeare. The librarian knows exactly what to do. Simple. But the trick request, that's where the magic happens. It adds a tiny but incredibly powerful piece of logic. It says, find me books where the author is Shakespeare or where 1 equals 1. Now think about that. When is 1 not equal to 1? Never. It's always true. So you've just twisted the librarian's instructions from find these specific books to find books by Shakespeare or, you know what, just give me everything because this other condition is always true. You've injected a brand new command right into the original request.
And that, right there, is the whole game. Now, let's take that exact same logic and see how it plays out in the world of software, where the stakes are a whole lot higher than just a pile of books. So here it is, the official definition. An injection attack happens when an application is basically built to be too trusting. An attacker sends what looks like normal data, like a name or a search term, but it's actually hiding a command. The application doesn't check it, it just passes that malicious command straight to something like a database, which then executes it without question. It is literally the librarian taking your or 1 equals 1 and running with it, no questions asked.
And let me be clear, this is not some small, obscure problem. According to OWASP, that's the Open Web Application Security Project, a huge nonprofit that sets the standard for this stuff, injection was ranked the #3 most critical security risk for web applications in 2021. This has been a top-tier threat for well over a decade.
So why does this keep happening? Well, it all boils down to a fundamental failure of trust. As you see here, it's caused by a few core mistakes: not checking or validating what a user types in, mashing user input directly together with database commands, that's called unsafe string concatenation, and just generally failing to use modern, safer ways of coding that are designed specifically to prevent this exact problem.
Theory is one thing, but this kind of vulnerability has led to some absolutely massive real-world data breaches. Let's look at a famous case to see how this simple trick turns into a high-stakes digital heist. So our story takes us to Yahoo's search. Back in 2013, a security researcher found a huge SQL injection flaw right in their main search engine, a system being used by millions and millions of people every single day. And here it is, the smoking gun. This is exactly what we were just talking about. The application was taking whatever someone typed into the search box and just pasting it right into the database command. This is the perfect digital version of our librarian who just blindly follows those tricky instructions without a second thought. So how did it all go down? It was shockingly simple. First, they found the flaw. The search box wasn't being checked. Second, the attacker injected a tiny bit of code. In this case, just 2 little dashes. Now, in the SQL language, 2 dashes mean ignore everything else on this line. This trick effectively chopped off the rest of the command the developers had written, letting the attacker's own command run instead. And just like that, with that one tiny trick, they had the keys to the kingdom, the ability to read, change, or even delete data in the database. The potential impact was huge. As this chart shows, it wasn't just one problem. You had massive data exposure, of course. Then there was the huge blow to Yahoo's reputation. And on top of all that, the risk that an attacker could gain control over their actual systems. It's a total nightmare scenario.
Okay, so we've seen the danger. It's pretty scary. But here's the good news. We absolutely know how to defend against this. So let's flip the script and look at how we build the digital shield to stop these attacks cold. This right here is the single most important defense. Look at the difference. The unsafe code on the left just mixes user input and instructions all together in one messy string. But the safe code on the right uses what's called a parameterized query. Think of it like this. It sends the command template, the instructions, to the database first. Then, separately, it sends the user's data. The database is never confused. It knows this is the command and this is the data, and it never mixes them up. The attacker's trick just doesn't work.
On top of that #1 solution, defenders have a whole toolkit.
You've got to validate all input, which means you only allow exactly the characters you expect, nothing else. You can use a web application firewall, or WAF, to spot malicious requests before they even hit the application. And you apply the principle of least privilege, which is a fancy way of saying the app's database account should only have the absolute bare minimum permissions it needs to do its job and not an ounce more.
All of these defenses, every single technique, they all point back to one fundamental, unbreakable rule. So if you take away just one thing from all of this, please let it be this.
This is it, the golden rule. You have to assume that every single piece of data coming from outside your system is potentially hostile. Whether it's from a user, another computer, anything, it must be checked, it must be cleaned, it must be handled with care. In security, trust is the vulnerability. And that kind of leaves us with one final big question. Our entire digital world is built on code, on instructions being sent and executed. But when anyone can potentially sneak their own instructions in, disguised as simple data, it really makes you think. Whose job is it to check those instructions? And what happens when we get it wrong?